All right, so here's what we've got today is we're going to transition from using graphical addition of vectors, which is cool because it gives you a sense of how these vectors work. And then we're going to transition from that into using trig functions. So the graphical addition is cool because it's going to save you a lot of heartache, because what you'll see later on is that your calculator will lie to you. And it's like, don't be sick. My calculator is my best friend. My calculator would never lie to you. Your calculator will roll you under the bus, okay? I'm just telling you. Shocking as that may be. But if you don't know how to draw the vectors to get a visual idea of how everything fits together, then the trig functions are just going to be a train wreck. So let me kind of take you through some of these, so you at least have an idea as, hey, does your answer seem reasonable? So if you look like on number 7, okay? So on number 7, you have B plus C plus D, okay? That's what you've got. So all I'm going to do is just make a crude sketch of this. That's all I'm going to do. So I'm going to draw vector B first, which is 3 centimeters at 90 degrees. Then I'm going to draw vector C. And then I'm going to draw vector D. So D is kind of the tricky one because of the fact that that's 250 degrees. So, and again, remember, that's measured from this positive x-axis. So you're going to start here, go around 180, then go down another 70. That's how you're going to get to that 250. Okay, so it's 70 degrees below that negative x-axis. Here's the whole part of the story. Isaac starts here, he walks up. He turns, he walks, and then he's going to come back down. At this point, he's right here, okay? This is what we've got. So what we've got to do is tell Dominic how to get to where Isaac ended up. So that resultant then is going to go from that origin out like that. And the resultant is what you are after. That's the end game of everything. So that angle, if you measure that around, and this is just a very crude sketch, that angle gets me around 170 degrees. So your answer to number 7 should be around 4 centimeters and around 170 degrees. Okay? That's a huge-ish, okay? But it should be something close to that, somewhere around 4 centimeters and 170 degrees.
Do you need number 6?
Yeah, number 6, I'm sorry, number 6. Okay. Number 6 should be around 4 centimeters and 170 degrees. Now, that's number 6. I lost track of that. That's number 6. So number 7, and again, all I'm going to do is just a sketch. So on number 7, you're going to go out 5, so there's A, and then you've got B, and then you've got C, and then you've got D, and then you have E. And there's going to be that result. Okay? So that's what number 7 should look like. A, B, C, D, E. And oddly enough, the answer to number 7 should also be around 4 centimeters and 170 degrees. Okay? Because if you think about it, what happens between 6 and 7 is that you're adding A and E to it on number 7, but A and E in effect cancel each other out because they're in opposite directions. So if you gave that a little bit of thought. Now, let's talk about number 8. And number 8 is going to form the whole basis in a roundabout way of forces, okay? And I want to show you the difference between these two diagrams. So number 8, you've got Bob, okay? So Ranger Bob starts off from base camp, and he's going to go out 45 degrees and 3.8 kilometers. Now, this is the classic situation where you need to set up a scale. Don't try and draw a line 3.8 kilometers long. 3.8 kilometers long would be about 2 miles, okay? That would take a lot of paper. So what you want to do here is what I would recommend is just do something simple where you let 1 centimeter equal a kilometer, okay? You just shrink in the scale. It's going to be the same ratio. You just shrink the scale so you're not drawing these lines incredibly long. So you got 3.8, and then you've got down here at 270, and then you've got, what's the next one, 225, which puts you something like this, and your resultant is going to go like this. Okay? So it's vital that you understand the difference between these two scenarios that I give you with Bob. So, and this is going to play out with forces as well, which is what we're going to really get into starting tomorrow. So if you're Bob, okay, and you're trying to get back to where you're starting, your angle is going to be measured from this positive x-axis, and you're going to be going up this way. If you're the search party, you're headed this direction, and your angle is going to be measured from that positive x-axis, okay? So they're both going to travel the same distance, but one is going to be measured from this positive x-axis. This one's going to be measured from this positive x-axis, okay? Now, here's the difference in terms of forces. So when you draw free body diagrams of forces, the beauty of force problems is that every force problem can only fall in one of two categories. Either the object is accelerating or the object is not accelerating. So here's the classic example. So if I hold up this 1 kilogram mass, and later on you see how I got this number, it weighs 9.8 newtons, because 1 kilogram times the acceleration due to gravity on Earth, you get 9.8 newtons. So right now, the mass isn't accelerating, because all of the vectors add up equal to 0. So I've got gravity pulling down at negative 9.8 newtons. Then I've got another vector from my hand acting upward. So if I were to draw them tip to tail, and I end up back at the origin, that means I'm going to have constant velocity, okay? I might be moving, I might be at rest, all I know is that I'm not going to accelerate, okay? So as soon as you see a force problem and you see, hey, it's moving at constant velocity, that's what would happen here. Bob goes out, Bob goes down, Bob turns, and then Bob ends up back at the origin. So if you draw all of the vectors with forces, and they end up back where you started, that means the object has constant velocity. Okay, so that would be boom, 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 and you end up back where you started. That would be like me holding this up. I got a vector pulling down of gravity, my hands providing an equal and opposite vector pointing up. I meet back at the origin, I don't accelerate. Now, if Bob stops down there, and the search party has to find him, and you don't end up back at the origin, that would be like me dropping this mass. I drop this mass, and it begins to accelerate, because I still have the downward pull of gravity, but I don't have the force from my hand balancing that out. So that's why I said, everybody says, oh man, forces are hard. I can only do two things with forces. I can either make you have a constant velocity and Bob ends up back at the origin, or you accelerate and Bob ends up out here and you have to go find Bob. Okay? That's it. Only two things I can do. Now, if you're accelerating, what's the only two things I can do with any acceleration problem? Speed up or slow down. So basically, every force problem only falls into one of three categories. You're either at constant velocity, Bob ends up back at the origin. You accelerate, you don't end up back at the origin, and then you either speed up or slow down. Every force problem is only three things. Constant velocity, you speed up, and you slow down. That's it. Those are your only three possible options. That's it. Oh, you see constant velocity. Make the forces add up to equal to zero. You see the word accelerate. The forces don't add up to equal to zero. That's it. That's all you have. If you remember that, you have about 80% of forces understood right there. Okay? Then you just have to figure out what kind of forces you're dealing with. Whatever you do, when you answer that, what is the relationship between the direction and magnitude of the search party's path and Bob's? So help me. If you have the word different in that answer, I'm going to flip out. Okay? Or it's not the same. Or the angle changes. Bad. Okay? Bad. Because it's different or it changes is way, 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 way too nebulous. Okay? I don't know what that means. Right? Now, you can say they're opposite of each other. I can live with that. Okay? But you just can't say the angles are different. Does that make sense? Okay. So, now we're going to get into trig functions. But we're going to do a quick little kind of diversion into this thing. So, let's say it like on vector C. So we're going to look down on number 9. Okay? And I'm going to show you two ways that you can find the answer to number 9. So in number 9b, you've got vector C, 4 centimeters at 120. So I'm going to use that as an example. So I've got 4 centimeters at 120 degrees. So if I were to just ask you to draw that vector, you would take the protractor and you would measure around 120 degrees and you would draw a line 4 centimeters long. And that would get you to that point, okay? So Sydney is here. She's going to walk 4 centimeters at 120 degrees, okay? That's one way to get to that point. You have an angle and you have a vector. Boom, there you go. But the problem is that we're going to use trig functions. And trig functions only work with what specific type of triangle? Right triangle. Well, right triangles, right? Trig functions, sine, cosine, tangent, and the Pythagorean theorem only work with right triangles. This is not a right triangle, okay? But here's the tricky part. Let's say that you go, Bergkamp, I was president of the Cartesian Coordinate Club in high school. That was my jam, okay? We walked in X and Y lines, okay? That's how we define systems. Cool, all right? Nothing wrong with a good Cartesian coordinate system. So, what you could do to get to that same point, it's like, Mr. Bergkamp, I love X and Y coordinates. Could I do this? Could I tell you to move a certain dimension in the X direction and a certain direction in the Y direction to get to that same point?
I believe so.
Oh, I think so. I could tell you to go out some negative value of X because it's in the second coordinate or second quadrant. And then I could tell you to go up to a certain point, right? So if Sydney walks out 4 centimeters at 120 degrees, I could go to Isaac and go, Isaac, well, how do you want to get there? He goes, Bergkamp. Coordinate systems, I like it. Cool. So I could tell Isaac to go some dimension in the X direction and some direction in the Y and get to exactly where Sydney is. It's just a different way to get there. Everybody see my point on this, okay? Same point, 2 different ways to get there. So what this is doing is called deconstructing the vector, okay? You have a vector and you find the X and Y components to get there. Now, some of them are very easy, so you got the idea. I actually started with a more complex one. Let's jump back to a simpler one. So if you look at vector A is 5 centimeters at 0 degrees, okay? So one way for you to get from this point out to this point is I tell you, you move 5 centimeters at 0 degrees. And you can get to that point, and it's valid, and it's cool, okay? But you go, Burkamp, let's talk Cartesian coordinates, okay? So what would the Cartesian coordinates, the x and y components, that would get you to that exact same point? 5 centimeters and 0. So here's my point. 5, 0, as an x and y coordinate system, gets you to the exact same point as 5 centimeters at 0 degrees. It's just how you want to define the system. So on this line where it says vector A, 5 centimeters at 0 degrees, the x component is just 5. The y component is 0. Okay, don't make it difficult. Easiest points you're ever going to get in this class.
No units?
Or centimeters. Okay. Now, vector B points straight up. So what's the x component of vector B?
0.
0. You have no movement in the x direction. The y component is going to be positive 3 centimeters. Okay? Same coordinate system. Now, let's talk about C. We need to talk trig functions. So, quick diversion and review of trig functions. So we're going to have sine, cosine, tangent. So what does sine equal? Opposite over the hypotenuse. Cosine is, and tangent is, they still teach Chief Sokotoa? And then we're going to have the Pythagorean theorem, a squared plus b squared equals c squared. Okay? Those are going to be the big equations that we're going to need from here on out. So the beauty of trig functions is that it takes out the ambiguity of measuring things. Okay? So how Ryan might measure a certain length and get the vectors might be different than how Michael gets it. Okay? Even though you're measuring the same, you might be off by 1/10 or 2. The beauty of trig functions is that it alleviates that uncertainty from measuring things. So let's start with something simple. Something simple. Let's say that I gave you a dimension of 6 centimeters and the angle was 40 degrees. That could be meters, it could be newtons, it could be momentum, it could be an electric force field. Doesn't make any difference. It's just a vector, 6 centimeters. And we want to find the x and y components using trig functions. Okay? So, let's start with the y component first, which is the side opposite. So what you'll always be given is the hypotenuse, which is the vector itself. So you're always going to be given the vector. You just need to find the x and y components of that vector. Okay? So, what trig function, knowing that angle, knowing the hypotenuse, and I'm trying to find the side opposite, I'm going to use sine. So I know the sine of theta is going to equal that opposite over the vector itself, right? Because the vector is going to be the hypotenuse.
Is that a what?
Huh? It's just the angle. Theta is just an generic angle. So, how am I going to get y by itself? Simply multiply. Okay, cool. So I got the sine of theta times the vector is going to equal the y component. Okay? So in this situation, I'm going to take the sine of 40 degrees times that vector of 6.00. On your calculator, make sure you are not in radian mode. Huh? If you hit like the home screen or something like that, mode maybe.
Then you should be in degree.
Yeah. Because if you're in radian mode, you are going to get answers that are so jacked up. Okay? They are going to make no sense whatsoever. So, somebody take the sine of 40 times 6. What do you get?
3.86.
What'd you get?
4.47.
4.47. Okay? Now, what did I
I
just?
just switched it, I swear I did. He wants me to do it.
4 point what?
3.87. You want me to do it.
Ironically, what'd you get?
3.86.
Oh, it's gonna be a long. Now, I'm gonna give you a lesson in history, even though this is physics class. So, and no, this was not my high school physics textbook. But it's cool because this book was published in 1902, 123 years ago. Okay? 1902. And in the back of this, but this is where it's relative to how I learned to do trig functions. In the back here, there's a chart, and every advanced physics and chemistry and mathematics book had this chart. And it was a chart of your trig functions. So how I learned to do trig functions, and this is going to be important, I would go through, like if I wanted to do this calculation, my high school physics teacher would not let us use calculators on the test. So if he gave us this problem on the test, I would go through here and I would find 40 degrees, okay? So the sine of 40 degrees is 0.643. If you don't believe me, just type in sine of 40. Let me know what you get. What'd you get?
0.6427.
Yeah, 0.6427, all these numbers. So what I would do, if I were to do this problem in my high school physics class, I would go to this chart and I would find the sine of 40 degrees, which is 0.643, whatever that number is. And then I would take that and I would multiply that by 6. And that's how I would get the answer. Okay, and I would do that by hand. It's like you're going, oh my God, Rick, that sounds so horrible. There are still colleges, some physics classes in some colleges do not let you use calculators on the test. Okay, they don't. Like you have to do the calculations by hand. That's not going to be me, but I'm just saying. So, what I learned to do is look at a chart. But this is going to be important. This chart only goes through 90 degrees. Okay, it stops at 90. Now, here's the other cool thing about this book. Here's the index. Okay, this is all the major concepts of the book. This is from 1902. If you go through this index and you try and find the words electrons, protons, or neutrons, the words do not exist. Okay? 1902, 123 years ago, we did not understand the basic structure of the atom 123 years ago. It wasn't until like the late 1900s that we found the electron, then we found the proton, then we found the neutron, then we found Rutherford's work with the gold foil, which we'll talk about tomorrow. So it literally, less than 100 years ago, we did not know the structure of the universe. We had no idea that atoms were made of subatomic particles. We thought atoms were the smallest possible particles. You look up like the Andromeda Galaxy, didn't know the Andromeda Galaxy existed. For up until like the 1920s, 1930s, we thought we were the only galaxy that existed in the universe. We did not know that there were other galaxies that existed because we didn't have good enough technology to find those things. So now we know that not only, we went from being like the chosen child and thinking that the universe revolved around us as the earth and the whole solar system revolved around us, and we thought we were cool, okay? And that's like mom every day, you're a senior, every day, mom packs your lunch and she sends you a note that says, you're special, love you, okay? So for 18 years, you've been told you were the chosen one. And that's what we thought for a long time. We thought the earth revolved, that everything revolved around us, okay? We were the center of the universe. And then imagine halfway through your senior year, you open up that same Scooby-Doo lunchbox, and there's a note that says, sorry, you're just like all the other kids. Okay, you're really not that special. That's what happened emotionally to us when we realized, wow, we go around the sun just like all the other planets. We're really not that special. We're just like Mars, Venus, whatever. We go around the sun just like all the other planets. They're like, well, that's a letdown. And then we thought, okay, well, we're still the only galaxy. We're cool. We're the Milky Way galaxy. We're cool, right? Cool, nice. Oh no, there are millions upon billions of other galaxies in the universe. So not only are we not special, we're not special by a long shot, okay? We're really not. So just keep that in mind when you go through your life going, oh man, my life is so hard. You are on a rock in the middle of the universe, one of a billion galaxies, okay? Just keep that in perspective. Okay. I'm just saying. So those are your short history lessons, and maybe a lesson in philosophy. Okay, so with that said, let's talk about this, what's relevant to you. So you have vector C, which is 4 centimeters at 120 degrees. Okay? Now, here's the thing. Again, you have to view this from my perspective on how I learned how to think through this process. This table of trig functions did not go to 120, okay? The table stopped at 90. I could not look up 120 degrees if I tried. Did not go there. Stopped at 90. But what could I do if that went to 120?
Multiply by 2.
It goes up to 180. 180 is the whole thing. So that means this angle in here is, now, 60 degrees I could look up, okay? I could find sine, cosine of 60. Could not find 120. So the advantage of working with the 60 degree, this is just a personal perspective. Me personally, I like to work off the 60-degree angle because it's easier for me to see if I use sine and cosine of 60, that this is the opposite side of 60 degrees. This is the adjacent side of 60 degrees. Conceptually, if you tell me this is 120 degrees and I'm trying to find the side opposite of 120 degrees, I would think that's like somewhere up here, okay? Side opposite of 120. Well, that's weird because it's somewhere there. Doesn't make any sense. Try and find the side adjacent to 120 degrees. Well, that gets weird too. Your calculators will handle 120 degrees. But you have to be careful in terms of making sure that you do have the correct sign. Since this is in the second quadrant, what's going to be the sign of your x component?
Negative.
Your y component is going to be positive. So when you do that, make sure that your calculator isn't lying to you. It's like, again, this is working out. My calculator is my best friend. It would never lie to me. Hide and watch. It will too. So let's make sure everybody's cool. So on that line, where it's got the 4 centimeters at 120 degrees. So if you want to just use 120 degrees, that's cool. So somebody take the sine of 120 degrees times 4 centimeters. And make sure that you're in radian, not in radian mode, degree mode.
If someone were in radian mode, how would you fix it?
Go to that mode button and you can. So what'd you get with 3 significant digits?
3.46.
3 point what?
46 centimeters.
For your y component?
I hope.
I do too. Because if not, this is going to get really weird. And then your cosine is going to be hopefully a negative number.
I got -2.
Exactly?
Yes,
Yeah.
exactly.
No, you didn't.
I did.
Oh, you did. That, I was looking at the wrong one. You did. I was looking at the next one down. You did. Because that's 60 degrees. Okay. So go through and fill out this entire bottom chart of X and Y components. The only ones you really need to use trig functions on are the 90 and the 250. The 0, the 90, and the 180 are all like on X and Y coordinate planes. So get that filled out. Ava, can you shut down? Thank you.